Good morning. This is the last class, and I want to finish with some applications in ceramics, but mostly in chemicals, the petrochemical industry. They have various types of reaction vessels. So if we look at ceramics, these are just furnaces for sintering. We talked about sintering earlier in the course. Basically, the sintering process is a consolidation process producing a strong ceramic without reaching the melting points. So these furnaces go up to about 1800 degrees C, and basically they're firing ceramic powder compacts of some type and going through the sintering process. The tunnel kilns are continuous, and the shuttle kilns are a batch operation. The continuous operation furnaces, you're usually running a car of some type through the furnace. So kiln cars, they'd be rather large cars on wheels. A roller hearth and a slab pusher are going to be flat plates that are pushed through a furnace. And the roller hearths in particular are rapid fire. That would be for thin ceramic objects like tiles. And then the shuttle kiln is a batch operation. So a tunnel kiln looks something like this. They're rather long. There's a preheat zone, a burning zone where the sintering takes place, and then a cooling zone. So this is one with a kiln car. You can see there's a railroad track system. So these are on wheels. They're pushed through the furnace. And there's no issues here with corrosion or thermal shock. So these are going to be lined with an insulating firebrick, an IFB, or some type of fiber lining. It could be fiber boards or it could be fiber blankets. The fiber blankets can be folded to create different thicknesses and attached to the wall. So IFBs or different types of fibers. So this is a cross section of the furnace. And then this would be a typical temperature profile. So there's a gradual ramp up in temperature. There's a hold. Um, that would be where the sintering takes place. And then there's a cool down. So these are usually gas fired. You can see the ports on the side of this furnace, and they're adjusted uh, to create this type of temperature profile. So there's the preheating zone, the sintering zone, and then the cool down or annealing zone. So in this firing zone, you can adjust the gas burners to be reducing or oxidizing. So if you can adjust the gas to air ratio, excess gas would be reducing, excess oxygen is oxidizing. So you could create oxidizing or reducing conditions. And then a shuttle kill is a batch operation. Again, no corrosion issues. There's no molten materials, no thermal shock issues. So they're, again, lined with IFBs, insulating firebricks, or some type of fiber insulation. So this type of furnace is loaded. There's a door that's closed. You go through the firing cycle, you open it up when it's cooled, and you unload the furnace. So the burners, if they're gas fired, can be various compositions. They're usually a high alumina. They can also be a silicon carbide. So this is a post-mortem of a burner nozzle. This is a 99% silicon carbide material, and this is a 20x magnification of the hot face. So this particular material is about 55% Si, 22% carbon, and 22% oxygen. because it is already oxidized, you have oxygen present. Normally, there'd just be silicon and carbon. So for the phases that are present, these were determined by X-ray diffraction. There's silicon carbide about 45%. So about 55% of the silicon carbide has disappeared. It's in the form of cristobalite, about 30%, tridymite, about 10%. We talked about these two high temperature forms of silica. And then there's a silica glass also about 15% is amorphous. So the silicon carbide has been oxidized to these two forms of silica plus an amorphous silica glass. So at a little higher magnification, you can see the individual crystals of silicon carbide. They're in the lighter gray. The darker gray that's highly microcracked is the oxidized material. So you can see the surface is oxidized and oxygen diffuses through the structure, attacks the silicon carbide at the pores, and it moves along the grain boundaries. So if we map this with SEM EDS, the silicon in this turquoise color, the brightest part is the actual silicon carbide, and then the lighter regions are the regions that are oxidized. So you can see easily on this micrograph, the red color is the oxygen. So you can see what's been oxidized rather easily. So the black is the intact silicon carbide, and then the red is what's been oxidized. So you can see the oxygen diffuses in, reacts at the pores, and then moves along the grain boundaries. And this is just a higher magnification. So here's a silicon carbide crystal intact. It's about 71% silicon and 28, 29% carbon. And this is stoichiometric silicon carbide, about 70% silicon and about 30% carbon. So this is unaffected, but the area between the crystals is oxidized. So you can see the silicon content's about 32%, carbon's about 17, and then there's a lot of oxygen present. Half of it is oxygen, 50%. So that's the portion that's been oxidized. So the turquoise again is the silicon carbide, the brightest part, and then the part that's less bright is the oxidized portion. And one thing to note, this oxidized portion is highly microcracked, so that deteriorates the structure. And again, the red here is the part containing oxygen, which has been oxidized. And we talked about two types of oxidation mechanisms for silicon carbide, passive oxidation and active oxidation. Well, this is passive oxidation. That's where we have high oxygen partial pressures. So what's going on here is the oxygen reacts with the silicon carbide, forms SiO2, and CO2 gas comes off. And now you're forming this protective SiO2 layer. So we have your silicon carbide, your silica layer, and then the CO2 coming off. But there's a big volume change here. Silicon carbide is 3.21 grams per cubic centimeter. And the products, the oxidized products are a lot lighter. Cristobalite is 2.32, tridymite is 2.26, and amorphous silica-based glass is about 2.2. So there's a large volume increase when this material oxidizes, and that's why we have all those micro cracks from all the stresses that are formed when this volume change takes place. So that was a silicon carbide burner nozzle. And the petroleum reaction vessels, I think I have about 3 or 4 failure analyses here from different types of vessels. But in in general, they're producing some type of hydrocarbon fraction from crude oil. So a distillation is a separation process, and then various chemical treatments using a catalyst. Um, there's cracking, which breaks down the molecules, polymerization, which builds up molecules, and when you rearrange the molecules, that's a reforming type operation. So most of these vessels are metal shells, and they're lined with the refractory material. They operate over a range of temperatures from low to high temperatures. The atmospheres are usually corrosive. There may be steam present, hydrogen present, various acids may be also present, and there's liquids present, and they may have entrained particles, so there's erosion type issues. So most of these vessels, and this is a fluid catalytic cracking unit, FCCU. Crude oil is circulated over some type of catalyst material. It breaks down the oil into various products. So there's a reaction vessel, and then there's a regeneration vessel. Um, so these catalysts, in this case, microspheres, uh, have a carbon buildup. So that carbon is burned off in this regenerator vessel. So that renews the catalyst. These vessels are designed to last 5 or 7 years. So here's one of those units. Here's the reactor. Here's the regenerator. Um, so this is where the catalyst is regenerated. There's various tubes that move the material and extract the products. The regenerator and the reactor are usually lined with an insulating castable, like an aluminum silica material. And then these different tubes are subject to abrasion and thermal shock. So they're lined with a dense castable, usually a fused silica material, because as we learned, fused silica has low thermal expansion. So it's good in thermal shock resistance. It's also acidic. So if there's an acid-base process, it's resistant to acids. And if it's a reducing condition, CO disintegration may be an issue. Uh, Carbon monoxide attacks residual iron in the refractory and forms an iron carbide. And that volume change when the carbide is formed disintegrates the refractory. So this is a castable. It's from a hydrocarbon reformer, and this is the hot phase. So there's some silica, alumina, and lime. So this is a high alumina conventional castable. There's quite a bit of lime, so there's quite a bit of calcium aluminate cement present. And so this is the hot phase after use. This bright spot here is actually a metal fiber. So this material was reinforced with a metal fiber to improve its thermal shock resistance. So a higher magnification right at the hot face. You can see an alumina crystal right here. There's another one right here. This porosity pattern to me indicates it was a tabular alumina product. That's the residual porosity. So this is a high purity dense tabular alumina. So that's the aggregate. And then this is the matrix. And there's two phases in the matrix. The lighter needle-shaped crystals are mullite. So that's about 75% alumina and 22% silica. And then the darker gray region is where the calcium aluminate cement is. So you see alumina about 76% and calcium about 23%. So this is a high alumina aggregate with a matrix designed to form mullite and the residual cement. So I put this on here. This is a thermal expansion trace. So when you're doing a failure analysis, there's other things you can do besides looking at it, the microstructure with an SEM, trying to figure out what happened to the chemistry. We showed some X-ray diffraction work, so you can see what happens to the phases. But this is an example of how to use a thermal expansion to see what might be the highest use temperature that this refractory saw during service. So a lot of times a failure analysis involves overheating a furnace. So this is useful for a castable only. So a castable is unfired before service. So reactions take place during service, and you can see them show up on a thermal expansion trace. So this top curve here is the heating curve, and then the bottom curve is the cool down curve. So we run a heating cooling cycle on this material to about 1500 degrees C. And the change in slope indicates a reaction taking place. So a little bit lower than 1200 degrees C, there's a slope change here. So that's where mullite forms. That's where these crystals are forming in the matrix. So I got temperature about 1150 where that slope change takes place. So we know that this refractory right here that we extracted from the hot phase did not see a temperature higher than 1150 degrees C, because if it did, that reaction would not show up as a slope change. So what this tells us is that the maximum temperature that the refractory saw in service at the hot phase has to be less than this number, 1150 degrees C. That may be useful or it may not be useful, but at least we have an idea. It had to be below this temperature. And if you continue heating, you see that it starts to bend over and shrink. Well, that's where the sintering process, the densification process takes place. And that's at 1400 degrees C. So that's way beyond mullite formation. So obviously the refractory didn't see this kind of temperature. And then you see it cools down, and then it follows a pretty linear slope. So all the mullite has formed. You don't see a slope change on cooling. So thermal expansion can be useful on an unfired refractory for doing some type of check on what might be the maximum temperature that the refractory saw. And also in this particular refractory, there's some metal fibers. And this is a cross-section of one of the metal fibers. It's a stainless steel fiber. So it contains CR, chrome, iron, and nickel. So about 24% CR, 56% Fe, and 15% nickel. So that's a stainless steel fiber. I thought I'd just show you what happens to these fibers in service. They oxidize. So this is a higher magnification of a part of the cross section of that fiber. You can see this oxide layer that has formed. And if you look at the chemistry of that layer, there's quite a bit of oxygen and chrome. So it's a Cr2O3 layer that has formed on this fiber. It's kind of a protective oxide layer. So the chrome has to be diffusing outward and reacting with the oxygen. So if you do the mapping here, green is CR. You can see it's present at the outer surface, and then underneath that outer surface is depleted. So the chrome is diffusing outward, reacts with oxygen to form Cr2O3. And then here's the oxygen in red. So you can see it's formed this oxide layer, mostly Cr and O. And then this is the oxygen in the aggregates outside of this fiber. And I also mapped Fe in blue. So the layer is on the edge here. So the iron does not diffuse out of the um, stainless steel, and neither does the nickel here in red. Just the chrome is diffusing outward and oxidizing. So that was a castable with a metal reinforcement. This is an insulating fiber blanket from a tunnel, a reformer tunnel. And this is the hot face. This is the actual hot face here. This is moving inward. So you can see the hot face is now discolored from contamination. So this is just a low magnification photograph. And if you look at the fibers, this is 100X. This might be some spherical shot particle right here. Maybe there's another one over here. And this is a 200 micron marker. So these are pretty fine fibers. And if you increase the magnification, you can see how they're starting to degrade. There's a deposition on the surface of these fibers. So here's the chemistry of a clean region. It's an AZS fiber, about 48% silica, 34% Al2O3, and about 17% zirconia. So it's a high temperature AZS fiber. And then the contamination that's starting to appear, SO3. So there's a sulfur compound, and it looks like it's also picking up some lime and maybe a little bit of iron oxide. So there are other areas that are even more contaminated. And I put down here in red what's really changing. So if you look at the areas of high contamination, it's a lime sulfur type material. So this is probably a calcium sulfate buildup on these fibers. You still have silica, alumina, and zirconia on both of these. The way the SEM looks at these materials, there's a certain zone that the electron beam reacts with, and you're picking up alumina, silica, and zirconia below the contamination. But it's mostly CaO, and the software picks out SO3. So there's quite a bit of calcium sulfate on the surface. So that was an example of a fiber material becoming contaminated, and eventually that will degrade. And this is a sulfur recovery unit, and it's operating at 1100 degrees F. So on these failure analyses that we've done over the last 30 or so years, sometimes a company will just give us a piece of refractory and say, tell us what happened. They don't even tell us where its origin was, what it is, what the operating conditions were. But at least we knew this was from a sulfur recovery unit, supposedly operating at 1100 degrees F. So we got some information here. So this is the cold phase. And we did a bulk chemistry by XRF ICP on the cold phase. It's silica, lime, and alumina. So it's a calcium aluminate bonded castable. And even on the cold phase, it has a sulfur contamination. Sulfur has diffused in the refractory through the refractory to the cold phase, almost 15% sulfur. The SEM analysis here is in elemental form, alumina, silica, and calcium, and you see the sulfur. And you have a high oxygen because it's not calculated out in oxide form, but it would be Al2O3, SiO2, and CaO. We also did X-ray diffraction, XRD, on the cold phase. So there's some alumina in the form of corundum, about 6%. There's quite a bit of mullite, 13%. There's raw kyanite, that's Al2SiO5, about 18%. So the temperature was not high enough, 1100 degrees F. It wasn't high enough to transform the kyanite into mullite and cristobalite. There's a small amount of cristobalite, a small amount of quartz, probably in with the kyanite. There's calcium sulfate. So the sulfur has reacted with the lime in the calcium aluminate cement to form a calcium sulfate. There's elemental sulfur, quite a bit, 20%. And then a amorphous, probably a silicate glass of some type. This is the coarse aggregate. It's alumina, silica, and oxygen. And then this is the matrix, alumina, silica, and lime, plus oxygen. So this darker gray region is where the cement phase is. The bright region is the sulfur that has deposited in the material. So the blue is aluminum. So you can see the blue and the coarse aggregate. The finer pieces of alumina in the matrix are a little bit higher alumina content, so they're a little bit brighter. So you can see the fines in the matrix. Here's another coarser aggregate, and here's a very large one. There's some free quartz in this material, so the brighter green is going to be the free quartz, and then the green that's not as bright is going to be the alumina silica combination. The yellow is the calcium aluminate cement in the matrix. Has to be in the matrix. And then that bright phase I showed you in purple, it's in purple here. That's where the sulfur has diffused into the refractory all the way to the cold phase. So then if we look at the hot phase, the bulk chemistry by X-ray, fluorescence, and induction coupled plasma, XRF-ICP. There's about 20% sulfur. So you see silica, CaO, and Al2O3. So you see the calcium aluminate cement bonding the alumina silica aggregates. And the SEM EDS analysis of this particular photograph, alumina, silica, and lime, and oxygen because these are in oxide form, and then the high level of sulfur. So everything that's in the brightest white color here is going to be the sulfur. It diffuses even into the pores of the coarser aggregates and in through the matrix. So if we do an X-ray diffraction at the hot phase, it's about 5% alumina, almost 15% mullite, and we pick up the kyanite again, about 15%. So the temperature was not hot enough to convert kyanite to mullite and cristobalite. We see again some residual quartz. That's probably in the kyanite. And we have some calcium sulfate and a great deal of amorphous material plus the elemental sulfur. So here's an alumina silica aggregate here. And then at the brightest white type color phase here, there's some alumina, some silica, but it's mostly lime, sulfur, and oxygen. So that's a combination of elemental sulfur and calcium sulfate. If you do the mapping in blue, that's aluminum. Um, Here's one of the coarser aggregates. And then apparently the aluminum oxide in the matrix was a little bit higher alumina content. So it's a little bit brighter on the finer material compared to the coarser aggregates. And you can see the coarser aggregates in green here, the silicon. So they're a little brighter than in the matrix. And these very bright green spots have to be either quartz or maybe even cristobalite. And then the yellow is in the matrix. That's the calcium from the calcium aluminate cement. And then the purple is the sulfur that is diffused into the material. It's primarily diffusing through the matrix, but it also diffuses into the open pores in these coarse aggregates that are quite porous. So these have to be open porosity on these coarse aggregates. And then just a higher magnification right at the hot face. This has to be a residual quartz because it's all Si and O, so silicon and oxygen. And this is an alumina silica aggregate. So there's alumina, silica, and oxygen. And then the lighter phase is the sulfur. So if you look at the chemistry of the lighter phase here, it's all sulfur. And then this area here, it's a little bit lighter gray than the coarser aggregate. That has calcium, sulfur, and oxygen. So that's probably the calcium sulfate. There was much more elemental sulfur than calcium sulfate at the hot phase. So you can clearly see the aluminum oxide aggregates, the coarser one here, finer ones in the blue color. And then silicon is in the green here. So these really bright ones are quartz or cristobalite. And then this one is not as bright, but that's the alumina silica aggregate. And the calcium is in the matrix. These brighter calcium spots are probably the calcium sulfate that's forming. And then the purple would be all the sulfur infiltrating through the matrix. So this was a castable from a sulfur recovery unit operating at a pretty low temperature, 1100 F. So you can do other things um, in a post-mortem study. In this case, density and strength was measured. So the density at the hot face was about 91 pounds per cubic foot. The expected density of this particular castable, we were told what type it was, should have been about 130 pounds per cubic foot. So the hot face is lighter than expected, and the cold crushing strength was measured at about 350 psi on the hot face. This castable should have been 2,000 to 3,000 psi after curing at this temperature, about 1100 F. So it's very weak, it's low density. So what could have caused that? Well, you're always suspicious about the amount of water that was added during installation. If too much water is added during casting of a castable, it's less dense and weaker because of the higher porosity concentration. Probably not a real problem in this failure analysis, but the sulfur is degrading the cement matrix. So it's reacting with the calcium to form calcium sulfate. That has pretty high melting temperature, 2660 degrees F. But the elemental sulfur S8 melts at a pretty low temperature and boils at a pretty low temperature. So this material is degrading because of the sulfur that it picks up. And I put one more example here of a chemical type vessel. And this is an autoclave lined with aluminosilica brick. So this is the hot face of this refractory in the autoclave. And this is a reaction where they're extracting molybdenum metal, MO, from an ore. So you can see right at the hot face, this bright region is some residual MO and a little bit of silica. So here's the residual metal right at the surface. Some of it has to fuse into the refractory in the matrix. So the chemistry here is about 90% silica, um, maybe 7.5% alumina. And then you have your typical impurities, CaO, MgO, K2O, Fe2O3, and TiO2. This did not start out as a high silica refractory brick. The alumina has been attacked in this refractory. So the yellow is the Si. So it's pretty uniform throughout the microstructure, whether it's the matrix or the coarser aggregates. The blue is aluminum. You can see the coarser aggregates. In the matrix, there are some little particles that are brighter, so that they probably had some alumina fines that were higher in alumina content in the matrix. And the red here is the metal MO. It's confined to the surface. So a little bit higher magnification. Here's a coarse aggregate. Here's another coarse aggregate, and then you have your matrix region. So they're both very similar at this point. They're both about 90% silica and about 7% Al2O3 alumina, and your typical impurities. Again, if you map silicon, it's pretty uniform. So the coarse aggregate, it was probably made from a clay, and it was probably bonded with the same clay-based material. So that's why it's uniform. There's some alumina enriched fines in the matrix. So we had actually had a new brick here, and we did a bulk chemistry by XRF ICP on the new sample, and it has like 35% alumina, almost 59% silica, and then your typical impurities that you'll see in a clay. So this was a clay-based aggregate bonded by the same clay in the matrix. But then the bulk chemistry from the hot phase and then the SEM from the hot phase show a different composition. So if you look at the Al2O3 content, whether it's bulk chemistry or from the SEM, it's down from about 34 to 9 or 7 or 8%. And so the alumina has been attacked and removed from the process, probably an acidic process. And what's left intact is a material with a high silica content. So this is about 87%, this is about 89%. So whatever process they were using to extract the metal, the MO metal, was probably an acid-based process. Silica is an acid refractory, it's resistant to acids. So it was not attacked, but the alumina is more neutral, a neutral it's neither acidic nor basic, so it was attacked first. So we also did X-ray diffraction on the new refractory and then the used refractory at the hot face, XRD. Prior to running X-ray diffraction, you usually run a loss on ignition. So this is probably run around 800 or 900 degrees C. You remove the volatiles. So the new material had maybe some water picked up, only 0.1% loss on ignition, but the used material had a high loss on ignition, almost 15%. So here is the corundum content, Al2O3, 0.6 in the new material. It's no longer present in the used material. Here's the mullite content, about 38% in the new material, and it's completely gone. It's been attacked, so it's not there in the used material. The kyanite is still intact. The silica is intact. The cristobalite is intact. So the mullite has been attacked, and there's a large increase in the amorphous content. So from 40 to about 67%. So the alumina has been extracted from the mullite, and there's some type of amorphous silica oxide remaining. Also, some of the potassium reacted. There's probably an acid containing nitrogen. There's a little potassium cyanide that has also formed. So I mentioned using thermal expansion traces to try to isolate maybe a maximum use temperature. This is percent linear change again versus temperature. This one only goes up to 500 degrees C. And this trace was run on a new material. So it goes up pretty linear and comes back down. There's a little offset, but nothing really is happening on the new material. It's reversible thermal expansion. But if we run a sample from the hot phase, it's quite different. This is again to 500 degrees C. So somewhere above 100 degrees C, we're losing material. That's the loss on ignition. So you're losing the material, it starts to shrink. So that could be a hydrated phase. Could be a hydrated silica where the mullite was attacked. It could be the potassium cyanide. But this just indicates a reaction is taking place. And then cooling down tends to be linear again. Probably should have been run to a little bit higher temperature. This would have been more linear on the cool down after we remove the volatile compounds. So this is just showing you where these volatile compounds are coming off in this temperature range between 100 and 500 degrees C. So thermal expansion is useful for various ways on a failure analysis. So I have just 2 slides here to finish up. I just wanted to say something about the Orton Ceramic Foundation. So Orton started out his career as a geologist. So this is just a little bit of history. He worked in the ceramic industry and the brick industry, and he realized that in this time frame, the late 1800s, that ceramics was really an art. It wasn't a science. Metallurgy had already made the transition from art to science, but ceramics hadn't. So he was working in the ceramics industry as a geologist and realized ceramics was just an art form. So he established the first department of ceramic engineering at Ohio State in 1894 to accelerate this transition from an art to a science, because there were a lot of issues in production of ceramics back then that were not understood. 2 years later, he founded the Standard Parametric Cone Company, which eventually transitioned into the Orton Ceramic Foundation. So parametric cones were devices, ceramic devices to measure temperature to aid in the sintering of ceramics. So he started that company in 1896. In 1898, he helped organize the American Ceramic Society. So these are three fairly large accomplishments. Also, during this time and during World War I, he was a brigadier general in the Army, served in World War I. So he was quite busy. He actually accomplished quite a bit in his lifetime. He died in 1932, and he left a will that established the Edward Orton Jr. Ceramic Foundation. So we're actually a trust in the state of Ohio, and we have this self-perpetuating board of trustees. So they're assigned by position. So one position might be the head of ceramic or material science at Ohio State. So who's ever in that position serves on our board. The board has 5 members. So today we're a trust in the state of Ohio. We don't pay any federal taxes, but we do what the will established. The will had 2 goals: to create this company, to make money, to pay salaries, and to invest in the company to keep the company going, and to give money away. And the second part of the will was to promote ceramic science. So how we do that is we give money away to universities to support research on graduate students. So the product is perhaps research that may be useful to advance the ceramic industry, plus also students that graduate and work in the ceramic industry. So that's what we're up to today. We actually have 3 businesses, 3 business units. We have that's still in existence, the parametric cone company. We actually make parametric devices to measure temperature. We have a thermoanalytical instrument department, and we have a refractory service business. So we have those 3 businesses today. On the last slide, this is a picture of Orton late in life. He lived from 1863 to 1932. So I thought you might like to see a little bit of background on the foundation and what we're all about. So keep in mind that we are a foundation, and the will was established that we serve the ceramics community. If you have any questions, you're all in the refractory industry, I assume. If you have any questions about refractories, you can always call me or email me, or you can call or email the testing services group. So again, keep in mind that we're a foundation and that we can be helpful if you need help. So thanks for listening in on this course. We have another course coming up in February on microstructures if you're interested. But again, thanks for attending. It's appreciated. So have a good Christmas, and maybe I'll see you again.
Thanks, Joseph.
Thanks, Greg.
Thanks.
Have a
Thanks for.
good retirement.
Thank you.